Hello everyone, welcome to this video. This is Saeed Ahmed from Toronto, Canada. The goal of this presentation is to present my implementation of the research paper that you see in the screen, right? So my goal is to present it in 20 minutes. That's what I will try in this video. Okay. Welcome to my presentation. As you can see, my presentation is on predicting stock price using graph theory, machine learning, and deep learning models. So this is the research paper that I've done this work. So I tried to implement this research paper as closely as possible and then try to extend it. That's what I will present in this video. So what is the problem? The problem is, as you can see, predicting stock prices. I mean, predicting correctly, right? Now, so there is theory, many stock prediction or many portfolios are based on this, that you cannot predict stock prices consistently, and at any moment the stock price indicates the fair price considering everything. As I told, many portfolios were built on this, and there are opponents who consider stock prices vary from their fair prices, and it is possible to predict it, right? Okay, at one point it was more difficult to predict, but now with the extent of data that we have and with the new technologies, the consensus is it's becoming more easier to predict stock market prices, right? So when we predict, what we do? Usually select some stocks, and using some time intervals, we predict them, and we use statistics and machine learning. So what this paper has done, it has gone way beyond that, and it used spatial and temporal relationships among the stocks to predict prices. To understand the spatial relationships among different stocks, they implemented some sort of graph depending on the correlations, and then spatial relationship is coming from there. And the historical prices, that's where the temporal relationships comes, and that is being used to predict stock prices. So this is some related work. As you can see, ARIMA model is statistical mostly, and then LSTM, support vector meshing, Holt Winters, Bayes, and all those are used for stock price prediction. SVM and LSTM, they usually work well. And in this paper, as you can see, so the stock, the relationship that is modeled into a graph. You can see a graph, sample graph from my work. And then this paper has used graph convolutional neural network and convolutional neural network combo and multiple blocks of them for the prediction of the stock prices, where this graph is fed as an input. So yes, I try to implement the approach as closely as possible. This is my approach. So in terms of data, like the paper, I also used the Fortune 30 companies out of the Fortune 500 companies. I used scraped data from Yahoo and also financial news data from Yahoo stored in Kaggle. I utilized that. I tried another data set, stock prices from the Kaggle. That was, I think, difficult to work with, and then it did not reflect the paper. So eventually I needed to find out scrap data from Yahoo Finance. Like any regular data analytics machine learning project, as for the next step, I try to understand the data and try to adapt the data for my project. And there are some little bit of missing values. I used interpolation for those missing values, and also treated those some missing and null values. I think there are two stocks. It didn't have any data in the stock market, Yahoo Finance, so I removed those two stocks. So that's how 30 became 28. Okay, so afterwards, from all the data, I kept the data that I just need, right? So stock ticker, date, and closing price. That's what I needed. Sometimes adjusted closing price can be useful. When I scrap data, I could just scrap for one, but I could also scrap others. But when I was using some other data set, it had many other features that I needed to remove and keep only the one that is relevant for this, right? It's more or less straightforward. From this data, like the paper, I also created some graph, input graph for my model. So depending on different correlations, Pearson, Spearman, Kendall, and also in the financial news, how they are mentioned in the article. So the graph for different graphs are made. And then I created those models, or created those models in Python, Jupyter Notebook. Some of the models I tried, GCN, CNN, MLP, GCN, MLP, Deep Graph, CNN. GCN LSTM, I wanted to, but I didn't go there. So I create this model and then input this graph into this model, plus also the historical time series data into this graph-based model. And I collected the results, right? And conducted different experiments to understand what how much I can get, what I get by fine-tuning the parameters and hyperparameter adjustments, and collected metrics in RMAC, mean absolute price error, and the mean absolute error in those metrics. So this is the graph that you can see I created. I think the Pearson correlation in the data, if greater than 0.5, then there is an S for Spearman if the correlation is greater than 0.4, like the paper, and for the Kendall correlation if greater than 0.3, I create a graph. And this financial news based data, this is the graph. I did not show the weight, but if two stocks are mentioned in 20 articles, then the weight will be 20. That's how it was done. So data set, as I told, I used Y Finance module to scrape data from Yahoo, Fortune 30, actually 28, and closing price for 2 years, and news data set. Stored in Kaggle, but from Yahoo news articles. So in terms of implementations, okay, models and platforms, you can see that I tried these models as I told before: GCN MLP, GCN CNN MLP, Deep Graph CNN, GCN LSTM, just using raw equation. Those are my intention, but I did not actually reach there. So the platform, as you can see, this is the platform that I used. A Network X for graph display, Analytic for financial news, Y Finance scraping, Stellar Graph, some graph library, GC, and all those things. And these are some other stuffs. Okay. So what is the result that I got out of all of this? So you can see that training and validation graph, validation plots. So the lowest one is the mean square error, then MAPE, MAE, and the loss. Usually validation followed training, and sometimes validation did better. So this is what you see. I think from left to right: Pearson, Spearman, Kendall, and the financial news. If you see the plot, the top one is for the 1,000 epochs, and the below one was the 14,000 epochs. And you can see in terms of performance, the financial news that performed better in terms of prediction. Then I would say Kendall, and then I believe Pearson, and then Spearman, right? In general, in the paper, the sequence was usually news, and then Kendall, and then Spearman, and then Pearson. Mine followed to some extent, but somehow, in some cases, it varied. Varied. Okay. If I use 10K epochs, then I can see that Spearman performed the best. And then I would say news, and then Kendall, and then Pearson. So the corresponding data, you can see it here. So I think first case means GCN plus MLP, right? Okay, the second case, you can see second case mean GCN, CNN, and MLP, right? It is the closest one, closest matching to the paper. So the paper used multiple blocks of it. I just used one block. And then another thing is the paper is not sure that if in the GCN there are multiple layers or not, but in this GCN there are multiple layers of GCN, and then so one layer of CNN, and then MLP. That's how my thing worked. Now you can see again, validation follows training, but sometimes it, I think mean absolute performance rate, it probably overperformed. And I think here are not much following, but still overall data looks better even these cases. Pearson, Spearman, Kendall, and News. So let's see for 1000 epochs. So I'd say Pearson performed better, best, and then I would say that Spearman, then I believe Kendall, and then News, right? One thing is, overall for this architecture, my perception is if I use higher epochs, I usually get better result, and it might be slightly different result than the lower epochs. Probably there are more things to do here. Okay, so it takes sort of more iterations, you can see. Okay, let me see. So yes, if below means below image, 15K epochs, Spearman, I would say, then I would say Kendall, and then Pearson and News seems very similar. Okay, this is the same second KGCNC in MLP, but 10,000 epochs. You can see the readings are usually significantly lower, and it probably matched with the paper as well. News, and then it looks like a Spearman, but I believe it's very close to Kendall. We can say that the result from the paper, it sort of reflects, or there probably is a reason. Anyway, so I believe they're very equivalent. And then the Pearson. And definitely the hyperparameter or parameter tuning can give us better results, or more epochs can give more results. So I think the point is the paper, achievement of the paper, we sort of can see that that might be something valid or acceptable result, the paper that has achieved. Okay. So in third case, when I try to use deep graph CNN, this is the 1000 epochs, and there is one another 10,000 epochs. So deep graph CNN, it's a model built into the stellar graph library. It uses several GCN, each of them has multiple layers, and then several CNN and this and that. So I just added an MLP at the end to make it a regression problem, right? Now, there are some couple of challenges. I think it requires many training graph, many testing graph, and many validation graphs. In my case, I don't have that variation, right? I just made one training graph, one testing graph, one validation graph. So that's how the result, I will not say impressive, or the correctness, I will not say that impressive, but it is a good thing try, right? So I could achieve different training graphs by using one for adjusted close, another for closing price, another for opening price. That's how we could create, or probably I could just divide the entire duration and create multiple training graphs. That's that way it could perform better. Okay, that was one challenge. And another challenge was giving the target variable into it. I just used the last one. So it looks perfection in terms of predicting, but I don't take it because I think the data and how we fit, it's not ideal, right? It will be something good to try and as a future work. Okay. So I'll do some more comparison, my work with the paper. So this is the architecture, as I previously mentioned. This is the architecture of the paper. Graph convolution is seen in multiple of the MLP. So in my case, let's say this is one of them. So GCN layer, and then MLP, Y GCN, MLP, and Y. That's what I took here. in this case, GCN, CNN, MLP. GCN, CNN, and then MLP. That's my second case. This is the first case. Okay. So you can see just GCN, CNN, MLP. I did not use multiple block. Okay. So there are some challenges. I gave before to create the second block. I think it was sort of challenging and confusing as well. And yet to get more details how this output from one layer is feeding to the second. I think the paper might have mentioned they combine the output of CNN and GCN and then feed to the next. But again, it can be the other way around. GCN output goes to the next layer and CNN goes to the next CNN. So and another challenge was matching those dimensionalities and everything. So that's some challenges were there. So I think probably some future work to improve upon. And deep graph CNN, I think it is a stellar graph. I think you can see GCN and that sort putting in all those things. I just started it. MLP for the prediction. Okay, this is this architecture that I tried, and this is the paper that I tried. I tried to match with the paper and also try to do a little bit more, extend it, right? There's something that I had in mind to do, but I did not eventually. So it looks like LSTM. It usually works better in prediction, and if I make with GCN and LSTM, it is supposed to perform good, and it might even overperform than the paper. There is a possibility, but I didn't try it yet. And the stellar graph library, it actually has some GCN LSTM built in, so it could be easier, comparatively easier to do it. So that's why I plan anyway. Another approach could be I could use the raw equations, the GCN, whatever it does with the data matrix, I think graph adjacency matrix and the feature, that is another matrix. So I could apply those equations and step by step do this multiple times. I believe once I implement one step, it could be extended in multiple layers. And I think that probably is something to do. And I believe that can give a good result for sure. Yeah, I don't try. I might have seen internet that people are trying to use these equations. Okay. Okay. So now I will do some comparison among the numbers. Okay, I'll compare some numbers in my, okay. So you can see GCN, MLP. Okay, so in terms of RMSE, so news is the lowest, and then Kendall, and then Pearson. MAPE, the rank is news, and then Kendall from a different architecture, and then Spearman for mean absolute error. News, Kendall, Pearson. News, Kendall, Pearson from the GCN plus MLP. So here I can see that GCN plus MLP overall perform better than the other. If you consider, let's see, all the first scores are on the GCN, MLP, and news, right? So yeah, 10,000 epochs. Let's see, RMSE. Okay, GCN, CNN, MLP that got the lowest RMSE, and then Spearman from GCN, MLP, and then Spearman from GCN, CNN, MLP. Okay, then for MAPE, the lowest one on GCN plus MLP, 31, and then Spearman, and then news from GCN, CNN, MLP, and then news from GCN, MLP. For mean absolute error, again GCN, MLP, and then Spearman, GCN, CNN, MLP. No, then news, and then this, right? So overall, we can see it's mixed up between news and Spearman and the different architectures. So overall, I might still say that GCN plus MLP might be still be doing better. Okay, yeah, and 1,000 epochs can be as good as 10,000 epochs. However, it might be the case that GCN plus CNN plus MLP might be giving better results when epochs are high. Let's go back and see. So the lowest RMSE here is 73, but here is 37.51. So we are getting better RMSE here. And for MAPE, 54, 57. So yeah, that's what I get. Okay. It might be almost 20 minutes. So I probably will need to do a little bit of more, probably on the methodology. I need to talk less there. So in terms of ranking, the paper has the news, Kendall, Spear, Pearson. To some extent, those are there, but I believe in my case, Causation and Spearman, they were close, I would say. Probably Kendall went sometimes Spearman, and then the lowest probably Pearson. So that's how I'll put it. So in terms of challenges, yes, finding the exact data set or implementing exact architecture, those are definitely challenging. And probably the platform, if I had a better platform, I probably could do more experiment and faster results. So that could make me help to get a better overall outcome. I had access to better platform. I just didn't get a chance to do it. And yes, as I mentioned before, that adapting all the data for the overall architecture, this was seems especially in the second step, right? So limitations, yes, the challenges are there. Limitations will be there. So mine did not implement exact architecture. It just went close and did not achieve as good performance like the paper, but I can try to tune it to get better performance. I think if you see these numbers, I think these numbers are usually lower than my number. Anyway, again, parameter optimization, fine hyperparameter optimization, and then making the architecture a little bit closer. That could make things better for sure. And my news data set is only 15,000 articles, and they used 1 million articles. So future work is definitely addressing these challenges. And also the paper had issues in exporting gradient problem, I believe, using the same architecture and the equations. So I might have the same. So there's something to improve on. So these are the references. I hope that you enjoyed the presentation. If you have any questions, I'll be happy to answer. Thank you. Bye.